Good morning, everyone. I hope you spent a nice day yesterday and you slept well. So today, as we introduced in the last section and in the emails I have been sending to you, we are gonna correct the exercises that you received on energy statistics and on energy modeling. So these were simple exercises to try and work again with the theory and methodologies that we have seen to report energy data, and so to calculate, for example, energy balances, but also on a simple exercise on energy modeling and projection on the transport sectors. I hope you had the time at least to look at the exercises before today, so you had already an idea, maybe some questions you want to ask us. And after Arnaud and myself will show you the solution to the exercises live, we'll leave some time for questions related to all the topics we have already seen. So please feel free to take your time to write down on the question and answer panel in the Zoom webinar tool any question you will have on energy statistics and modeling, also on things that maybe we didn't see yet in the course. Of course, if we cannot answer myself and Arnaud because it's very specific to certain topics, we'll come back to you with an email after consultation with IEA experts. So thank you very much. And I think we can start with the first exercise, the one on energy statistics. I'm gonna share my screen now with the Excel file. Also, after this section today, we will send to you by email the solutions of the exercise. So a file exactly as the one you are seeing now in my screen with the exercise not solved and with the solution with all the calculations and also some answers written down to understand better why the calculations are made this way. So in the first exercise, you had some statistics from a country. This is on natural gas. I know in Ethiopia is not the biggest fuel, but this is just an example to work on some energy statistics and data calculation, estimation, and verification, let's say, of the data quality. So you had firstly an interesting table or balance, let's say, of natural gas. You can see, really important always when you look at a table, the units. You can see that this is in cubic meters, so a million cubic meters, so it's physical units, it's not in energy units. And you have both the supply, so production, trades, stock changes, and the demand side. So the consumption, then the consumption in the different sectors, but also the transformation into electricity in electricity plants. The first question said to transform all this table that is in physical unit, as we have seen, into energy units. So in this example is in terajoules, by the use of the provided gross calorific values that you can see here in the green table. To do that, what is required? First of all, you see you have different calorific values. As you have seen many times in the course, even the same fuel, in this case natural gas, can have a different calorific values depending on its specific components. So for example, a natural gas coming from a specific source or a specific well has a different calorific values and properties than a natural gas that is coming from another source. So here, for example, we can see that the production gross calorific value in megajoules per cubic meter in this country is around 38 megajoules per cubic meter. While the imported one, so maybe it's coming from another country, it varies a bit year by year because maybe it's coming from different countries. So depending on the relative weight of each of the imported natural gas, these calorific values varies. So the mix of the imported natural gas differs every year. And here instead for the production one, as we can see that for all the years is kind of stable, we can imagine that in this country, natural gas is always produced in the same well, so from the same source. So it's not really changing much. What we need to do here is, as I said, using these calorific values, convert all this physical balance table, let's say, or statistic table, in an energy balance for natural gas. So we want to report all these figures we say here in cubic meter, we want to report them in terajoules. So to do that, what we need to do? First, we need to calculate the weighted average calorific value, the gross calorific value, because as we have seen, we have one for production, one for imports that are different. And when the gas enters the countries and is consumed in their end-use demand sector, like industry, residential, this gas is mixed, and it's difficult sometimes to know exactly what is the calorific values used in the industry. Sometimes you know, and if you have the information, you can use a specific calorific values, for example, for the final use industry or the final use residential. But in the absence of this information, you can calculate the weighted average of the calorific values of your supply and apply it to your demand. So the first exercise required to calculate a weighted average calorific value for the supply of natural gas in your country. To do that, you need to consider for every year, so from 2013 to 2019, because production in the country, as you can see, starts only in 2013, and prior to that, we had only imports of natural gas, so no need to have a calculation here. So what happened is that we need to take into account the relative weight of the natural gas coming from production and the one coming from imports, and the different calorific values for each of them. So to do that, there is a specific formula that I can show you from the solution file that practically multiplies the production quantity by the production calorific value. You sum it with the imports quantity multiplied by the imports calorific value, and then it divides by the total of production plus imports. So doing that, you will have an average, but that takes into account the fact, the mix of these natural gases. So which of the two natural gas sources, production and imports, is having, let's say, a higher impact on the final supply. In this case, you can see from 2013, where production was still low in the country. So for example, start producing in November. So we had only 2 months of production in 2013, and it was just the beginning of this production, so it was lower than the other years. We can see that the average weighted calorific value is very close to the imports calorific value, because the relative weight of imports into supply is much higher. So we can see is 150 on 9 for production, so it's much higher. However, we can see that production in the country continuously grow till in 2019, where we have higher production than imports of natural gas. We also have some exports because the country is starting to become more self-sufficient. What happened is that the average weighted calorific values now is different than in 2013 and is closer actually to the production, because the weight of production of natural gas is higher than the imports. So calculating the weighted calorific values is very important to help then calculate the correct energy content of the physical quantity of a fuel. So in this case, natural gas in cubic meter, we are converting it to terajoules, that is an energy unit. So the second question was actually asking to use these calorific values and create this table in energy units. How would you do that? How would you approach it? Here there is some advice or a hint that say you, of course, for production, you can directly use the calorific values you have that is specific for production. Same thing for imports. You have a specific calorific values. And then we say for all the other flows, you can use the weighted average. Since we don't know, for example, for this country, what is exactly the mix of natural gas used for electricity production, for the industry or residential. So we can use this weighted average as a solution to have a better estimation of the energy content of the fuels consumed in each sector. So to do that, in the solution, we can see the formulas. We multiply simply here the quantity in cubic meters per the quantity, per the calorific values in megajoule per cubic meter. And we obtain our terajoule. There is no other calculation or multiplication to do, because the units from million cubic meter multiplied by megajoules per cubic meter will give us directly terajoules. But you need to pay attention that sometimes this is not the case. So you might need to adjust to the correct order of magnitude. For example, if you had, for example, gigajoules instead of terajoules, you would have to multiply by 1000 this multiplication if you wanted to report in gigajoule. So after you fill all your table, as you can see, here we use the production, here the import, and for all the other fuels, we are using the weighted average calorific values that we calculated. Then we had another question that here it started to be interesting because we start to analyze this data and try to look for mistakes and then solve them. Question 3 was asking to use this balance and calculate a verification indicator for statistical difference, so the difference between supply and demand. This indicator, a good one to estimate the weight or the importance of the statistical difference and assess if this is a problem for the data we have. As we have seen, a good indicator is dividing the statistical difference by the total supply. So for example, in the solution, you can see the formula. We calculate the statistical difference first. That is, I think, already calculated by the formulas here. Yes, is the difference between demand and supply. And then we divide it by the total supply. As you can see here, for many years, we have -2%, 1%, 3%. That is kind of okay. However, in question 4, we are asking to check the statistical difference and look if there are some years that shows a mistake. Indeed, in 2015, we can see that the statistical difference indicator is -55%. Here we can see in this graph a bit better. So the statistical difference is -55% in 2015. This means that there is a big discrepancy between demand and supply for this specific year. And so it means that there is probably, actually there is a problem either in our reporting on the demand side or in the supply. There can be like an over-reporting, a double counting, or an under-reporting. So for example, some flows or part of the consumption or the supply that has not been reported here. So this is very suspicious. We highlight it, and then we need, at a point, try to understand why this is happening and how this can be solved. Oops. After, we had another question. We already have question 4. And, okay, the question 4 also asks us, what can be the possible reasons for this statistical difference? Something that I was saying before, it can be that the supply is higher or the demand is higher, but we are missing some of the data because it has not been collected, double counted, etc. is what I was just saying before. After that, we go to question 5, where we can see we have a nice table on electricity production in the country by the different sources. So we have, this is not input. It clearly says output of electricity in gigawatt hour. So this is not the natural gas used to produce electricity, but this is the electricity produced by the use of natural gas. So as you know, there is an efficiency involved. You burn natural gas, you have some losses through heat losses, and then you will have your electricity output. This is important to remind before doing any other check. So using this natural gas table we calculated and the electricity data that we see in here in yellow, and also the conversion factors provided here to pass from gigawatt hours to terajoules, because the units reported for electricity and the units we used for the natural gas are different. So this is really another important thing to always take into account. We should look at the unit, and when we calculate ratios, like the efficiency, for example, we need to convert always everything in the same unit. So here we have the conversion from the gigawatt hours to the terajoules, for example, for this case. So using that, calculate electricity generation efficiency for natural gas. So how would you do that? As we have seen in our course, efficiency of the transformation sector, so in this case, electricity generation, is calculated as the output in energy units divided by the inputs in the same energy units. So this will give us an idea of how much of the energy we are using to transform in another type of energy, in this case of electricity, is really transformed and not lost. So when we do the calculation, as you can see here, we are taking our output, natural gas electricity production in gigawatt hours. So we are dividing it by our natural gas input to electricity production. So this is really the natural gas that is burned, converted to the same energy unit, gigawatt hours. So here we can see that we have 30%, 31%, we have some efficiency calculated. In question 6, however, we are asking if looking at this efficiency, we see some issues and where these could come from. There is also a hint to help on the exercise that says to take into account when we calculate efficiency, which are the numerators and the denominator for calculating it. So as you have seen is the inputs and the outputs. Easily we can see here that the outlier is in 2015 because the efficiency is dropping from a timeline of 30–35% to a much lower value of 20%. Another suspicious thing is that this is the same year 2015 as we have noticed the statistical difference very high. So we might start to think that these two problems might be related. This is very important when looking into data quality, to try to find what are the problems and how different problems are related to themselves, because this can bring after to the solution of the problem. So noticing some issues, yes, of course, we noticed 2015 is much lower than historical, and also is a low efficiency that we would not expect from natural gas electricity production in general. And to try to find what is the possible mistake, we can look above the electricity balance and the natural gas balance in this case. If you can see electricity balance, we have a total generation in 2015 of 1,850 gigawatt hours and a consumption of 1,822. So the statistical difference for electricity is very low. This makes us think we can make the hypothesis the electricity data are maybe correct. So we can look on the input side on natural gas, and we knew that there was this big discrepancy between demand and supply for natural gas. So we can start thinking now that this is maybe due to the fact that input to electricity plant is strong in 2015. Indeed, we can see that it's much higher than the other years. We passed from 5,000 to mostly 8,000 and then back to 6,000, while electricity output is mostly stable. It's not varying as much. So in the last part of the question, of the exercise, sorry, we ask to correct the wrongly reported figure. So we have seen that it's probably the input of natural gas to electricity production. So how can we do that? The hint tell, in absence of other information, of course, the best approach will be contacting again the data providers. In this case, can be an electricity plant, a gas electricity plant, or an electric utility if you have several electricity plants, of several electric utilities or electricity producers in the country. But in this case, we can tell that we don't have any answer from our data providers, so we don't have a contact there for the moment, and so we cannot solve the problem directly with them. And we can try to have an approach to fix quickly the problem by ourselves. But of course, the problem will need to be fixed better after by using the information the data providers will have. So how can we approach it if we want to solve it by ourselves and quickly? Quick and maybe a reliable solution will be to try fixing the efficiency. So we can say that 2015 efficiency will fix it as in 2014 or 2016, or we can do an average of the other years. We can have different approaches. So if we fix this at 35% as the other years, this means that, as we said, the input is the part that is not correct. This means that we can change our input. How do we change our input now? So we can say that our input to electricity is equal to a 35% efficiency of production. Okay, these were, here we are in gigawatt hours, so it's not correct. And we have to convert back to terajoules. So I think we have to divide by the conversion factor. Oh, there is something wrong.
Gianluca, I think you have put 0.35%.
Ah, yeah. Thank you. That was the problem, actually. I put the percent above the 0.35. So either you put 35% or either you put 0.35. Thank you, Arno. And now, I have to put also parentheses, of course, because if not, it will not work. And now, as you can see, our efficiency is fixed at 35%. And also, we can see that this is also solving our first problem of statistical difference from the natural gas balance, because this imbalance between supply and demand was caused by the electricity plant's inputs. Most probably, of course, this is what it looks like, and it strongly looked like that, but you have always to investigate with data provider to ensure this is the case. But here, as you can see, as we saw, we fixed a bit the input to electricity plants, also the first problem we spotted got fixed. As you can see first in this graph, we have a big imbalance between demand and supply, and now in 2015, we have a really, really low statistical difference of -2%. Same thing for electricity efficiency, production efficiency. In 2015, we have no more this big change in statistical difference we have seen before, in efficiency we have seen before, and we don't have this big spike in input. So if you have any question on the exercise, I think we can have them now. If not, we can move to the next exercise. I see there are some chat questions. Ah, yeah. Thank you, Abdul, for also telling us about the 0.35 and not putting both the percentage and at 0.35. We receive your message. So I think I'll pass now. If there are no questions or no, you can confirm to the second exercise, still on energy statistics. So the second exercise was to create a complete energy balance of the country. So with all fuels and all sectors, let's say, of flows. This is a simplified energy balance, of course, because there are not all the different end uses, not all the different transformation sectors, but it's still a complete set of data, because some of the other consumption sectors are included or aggregated in one flow only, as well as for products. As you can see here, we have only oil products altogether, but we could have all the different products like motor gasoline, diesel, etc., explicit one by one. So, but for the purpose of this exercise, it was not really important to have all the details, but the important thing was to make the exercise to try to report everything in the standard definitions of an energy balance. So what we need to do here is starting from question 1 that asks why coal and electricity plants in crude oil refinery cells are negative. So I'm not sure you can see, okay, yeah. You can see that coal electricity plants is negative, as well as crude oil input to refinery is negative. Why is that? This is transformation sector. There are electricity plants, and refinery sector is as well a transformation sector where you transform different kind of oil products like crude oil, natural gas liquids, etc., into finished oil products as gasoline, LPG, or others. So the why is because the negative sign tells us that this is the input flow, is the input product, so it's the product that has been consumed for transforming into another product. We can see in the example really quickly for the refinery, where crude oil has a negative sign because it's the input or the fuel used to be transformed, while oil products are positive because they are the output, and so the fuels that are produced. This is because it will be easier to spot the different inputs and outputs. Also, it will permit to easily calculate efficiencies of the transformation sector. It will also permit to easily know if for these products we are adding from the transformation sector more for the consumption side finally, or if we are removing some. So for example, for crude oil, as you can see, we have 500 terajoules, and then we are removing 495 for consuming in the transformation sector of refining. So we had still a 5 that could be consumed somewhere, or it can be just a statistical difference, as we have seen previously, because of the reporting and data collection in the supply side and the demand sides are different and sometimes come with discrepancy. And this is normal if it is limited to certain extents. So this is why the numbers are negative or positive. And then the second question was asking really to do some calculation and use the results from the exercise 1, the results, but also the data provided, to completely fill this table and using terajoules as unit. So what you need to do is complete the table with the natural gas that we calculated before, the natural gas and energy unit, the balance, then complete the production of electricity that we had in the table as well, as you can see here, for the different sources of electricity production. So here we can put the electricity generation, you see, in gigawatt hours at the end of the balance to give some more information. And then there are other parts to complete. One is the total electricity from electricity plants. The other is hydro, PV, and wind input to electricity plants and production. So what can we do to do that? First of all, I will show you the links. You can directly link your, for natural gas to the exercise solutions or the results you had in this table in terajoules. Actually, I see something wrong in the formula I put here. This is not correct because, as you can see here, we say net calorific values, so NCV. While here in the table we calculated, we used a gross calorific value. So this table we calculated is based on a gross calorific value basis. So it is a bit higher than a net calorific value basis. And we need to take into account when we calculate an energy balance if we want to show it in net calorific values as here. So this formula should be corrected by the difference between gross and net calorific values that for natural gas is around 90%. So I would multiply by 0.9 or 90%. And the same for all the different flows. Now, I will not take the time to do all of this now, but it's good that I realized this because it's an important thing as well to always know, even if in energy unit, what is the basis of the calorific values used. Is net, is gross, and to take action to make sure we are using the correct one. So after you filled all this by using the table that we fixed before, important is to make sure that the input electricity is negative. As we have seen before, the transformation inputs are negative and the outputs are positive. So we have to make sure this is the case. We report then directly, because this is in gigawatt hours here and was in gigawatt hours else in our table in exercise 1, we can report all the production of electricity by the different fuels. So as you can see here, we are speaking about the year 2019. So we'll go to the column L, 55. L is 2019, as you can see. And we take the production of electricity by the use of coal, by the use of natural gas, etc. And we report it in our balances table at the bottom. As you can see, we have hydro, PV, wind, etc. Then what can we do? We can also report electricity production. But here we are again in terajoules. So since the figures reported in exercise one, are in gigawatt hours for electricity production, we need to also convert this to terajoules again. So we use the conversion factor that I think we put again here, that was already in the other exercise, to convert the total electricity production, 1,427 gigawatt hours that we can see here in the exercise 1. We report it also as output to the transformation sector, you can see here, as a positive number, and also in terajoules, because our table is in terajoules. So this is why we multiply again by the conversion factor. after that, we have to report the inputs to electricity plants by the different fuels. So for natural gas, it was easy because we already had our figure. But what about hydro, PV, wind? We have seen in the presentations we had, I think, last week, when we saw energy statistic by product, that we need to put a convention for the efficiency of electricity production by these, let's say, electricity only generation sources, like can be hydro, PV, and wind, where there is no combustion. So if you remember well, exactly for hydro, PV, and wind, we said that we'll take into account an efficiency of 100%. This is a convention the IEA does, but there are other ways to do that if you want to apply. So in this case, if you apply an efficiency only of 100%, means that the output is equal to the input. In this case, there are no losses, and that we have just to convert our figure in gigawatt hours to a figure in terajoules, as you can see for all of them, and put them, of course, in a negative sign, because this is an input to electricity production. Okay, I hope this is clear. This is a convention that is 100%. What we consider for hydro, PV, and wind in energy balance is that the first point of measurement is the electricity output. We don't want to report the energy content, for example, of the water that is stored in a basin from a Niger dam, or the energy content of the sun irradiation hitting a photovoltaic panel, because this will bring much more complication and will make more difficult to understand our energy balances actually. So it is good that here we report some units, or let's say some figures that are related to something that we understand and we can measure easily. That is, in this case, the electricity output. As we have seen in the case of nuclear electricity production or geothermal electricity production, or also solar thermal electricity production, the first point of measurement was heat. So the heat produced, for example, in the nuclear reactor, or for example, the heat collected by the solar heat collector, or the heat extracted from the geothermal source. In this case, we also applied specific efficiency to transform from the electricity output to the input in terms of heat. That was, I think, around 33% for nuclear and maybe 10 or 20% for geothermal. But these are just the convention the IEA is using. You need to be sure that you use standard international definitions for this energy balance construction, but at least that you document how your balance is constructed. For example, here I'm telling you that for hydro, we use first point of measurement is electricity, and we consider 100% efficiency. So this is okay, this is clear, we know, and we can read the balance. But if you're using also a different approach and you're not documenting it or providing the information to the users of your energy balance, there can be some problem in the analysis that can be done with the energy balance, and so can bring to some mistakes. So this is the importance of documenting methodologies, of metadata that explains how each data is calculated, definitions of products and flows. And as I want to remember again, there is a document that established, let's say, all the definitions of energy statistics that was created by the UN statistics, the IEA, Eurostat, and many, many other organizations working on energy data. That is the International Recommendation of Energy Statistics, the IRES, let's say, document that is really important to follow if we want to create energy statistics that are in line with international standards, and so can be compared with statistics that are generated by other entities or countries. So say that, we have seen that we just convert our output to the correct unit in terajoules, because efficiency 100%. And then also the production will be the same for hydro, PV, and wind. So to calculate our supply, is important that we put also a production of these fuels as a national, let's say, energy generation. So we'll take part of our total energy supply. I'm speaking a lot, I'm a little losing the part where which question we were.
Yeah, Gianluca, maybe before shifting to the next question, we had a a short question from Abdul Yusuf
Yes.
on calorific value, referring to what you said on the difference between gross calorific value and net calorific value. So Abdul Yusuf was asking, is net versus gross synonymous to dry versus wet basis? From the definition of gross and net calorific value, as you may remember, when you burn a fuel, there is water vapor that you cannot use as an energy and which is lost. So when the gross calorific value is the value including this water vapor, so maybe it's a good way to consider it as wet, versus the net calorific value is just the useful energy, so withdrawing the water vapor. So maybe it's good to say dry as an analogy. Gianluca, I don't know if you want to elaborate more.
Yeah, the analogy can be correct, but you need to pay attention that sometimes dry and net energy content refers as well to wood energy consumption sometimes. So it can be misleading, but it can be a good approach, because when you burn wood that has a high content of water, the calorific value is much different than if you're burning wood that has been drying in the sun for some months or years. So this is also something that can be used for the words dry and wet. You can see I'm burning dry wood or wet wood, but it's not related to net and gross. But it can be an analogy, yes, as Arnaud explained, because the difference is the water vapor energy that is lost during combustion. Another way to call them is also higher calorific values and lower calorific values. Anyone call them in a different way, but they are the same thing. Sometimes you can see HCV for gross calorific values and LCV for lower calorific value. I saw the same as net calorific values. Thank you very much for the question, and Arnaud also for spotting and answering. Now I think we can continue to question 3, if you're all okay. So the question 3 asks to look into refinery transformation. So we have seen before, we have the inputs and the outputs, and to analyze if you see something wrong. I'll let you some seconds to think about it if you already didn't do the exercise. So why I could see something wrong? I see an input here of 495. That's okay, it's negative as an input. And then I see an output of 532. And I don't see any other inputs here. So practically this balance is telling me that I'm creating energy out of nothing because I have more outputs than inputs. And so this is not physically possible, and this is not possible also to be reported in energy balance. It means that there are some data issues. We can also see that in the total column, that is a very useful column, as we have seen us in the questions and the explanation we had in the presentations last week. Actually, yeah, last week on Thursday, I think, when we saw balances, a total column in an energy balance for the transformation sector cannot be positive, because if positive means that the output are higher than inputs, and means that we have a creation of energy out of nothing. So this is not possible, this is a mistake, and we need to find out why. So I can see here, we also ask to calculate the efficiency here in a specific cell. So we do output divided by inputs, and we get 107%. So 107% is again saying the same thing. We are creating 7% of more energy than what we put in as input. So it is not possible. So this was practically the answer that we wanted to hear, but then we also try to ask why you think is probably wrong. And here we give some hints on why it could be. We don't know why, but some hint can help also to investigate later and to ask questions maybe to the data providers. In this case, can be a refinery or an oil company. So this means that either the oil products output or the crude oil inputs are wrongly reported. See, this we understood. But what can be coming from? It could come from the use of wrong calorific values that will make either our outputs higher or our inputs lower than what they really are. or incomplete observations. So for example, we are missing some of the input that has not been reported, or we are, for example, counting 2 times the same output. For example, in these oil products, we are counting 2 times LPG because reported by different companies and is coming to this table wrongly 2 times. So this is why the output are higher. So these are possibilities of reasons for these mistakes, but of course, this needs to be investigated further. Now there is another question that I think can be interesting, is about CO2 emissions estimations. And this is also to show you that when you have a correct and complete energy balance, you can estimate CO2 emissions from fuel combustions in your country with a good level of, let's say, confidence, by using, for example, the IPCC 2006 guidelines, as we have seen last week with our colleague Aidan. So here we ask to calculate for total supply, so for the total energy that is coming to our country here, and also for electricity generation for each of the fossil fuels, what are the CO2 emissions? Why for each of the fossil fuels? Because as you have seen last week for CO2 emission estimations, when we speak about energy-related emissions, we consider that only fossil fuels generate emissions. Of course, biofuels, when they are burned, they generate some emissions, but this will be reported at the national level and international level from the change in land use, from deforestation, and so is a reporting that is made separately from the energy-related CO2 emission reporting. And to avoid double counting of CO2 emission reporting, the IEA and good standard when you report emissions related to energy, biofuels emissions are considered 0. So this is why we consider only emissions of coal, natural gas, and all the oil products. So here you had some tables with carbon emission factors from some different sources that the IEA has, but these are just figures that we use from the IPCC guidelines. But of course, coal can include different type of coal, so can be different, as well as the other oil products. So it's just some average. So what do we do here? We calculate the emissions for total supply. So how much the total supply of coal when burned will emit. So we multiply our total supply in terajoules by our carbon or CO2 emission factor, let's say. That is in tons of CO2 per terajoules. Then we divide by 1,000 just because we want the figure in megatons of CO2. We do the same thing for natural gas, for crude oil, and for oil products, for the supply. Okay? Then we'll do the same thing for electricity generation. So how much the generation of electricity is responsible for CO2 emissions in the country. So we have our energy balance. We know all the inputs of our fossil fuels. In this case, for this country, we have only coal and natural gas in 2019. So the only electricity production for which we consider emissions are these 2 products, coal and natural gas. And as I want to remind, these figures are negative and represents the fuel that is burned in electricity plants to be transformed to electricity, to be converted to electricity. So we can just multiply this, again, the example for coal, the input, by our emission factor of coal and natural gas, depending on the fuel you're analyzing. And so you'll have your emissions again related to electricity production for the different fuels, and also the total. As you can see, most of the emissions in this country are coming, more than 2/3 actually, are coming from electricity generation. The others emission will be coming from the final consumption. As you can see, there is coal consumption in the industry, there is natural gas consumption in industry, residential, and this will be, as well as oil products in transport, and this will be the other causes of emissions. So the difference between our electricity generation and total energy supply. Then what we ask after having calculated that, so this was a simple example to show that if you have a good balance, if you're using the good emission factors, you can estimate CO2 emissions. This is very important for reporting, very important for tracking policies or low carbon policies or other sustainable energy development policies. What else we were asking here? This is a really interesting thing as well to calculate. We are about electricity emissions related to electricity production, sorry. We are asking, can you calculate an indicator that tells us the intensity of electricity generation in the country in terms of emissions, or the emission intensity? This means that we want to know how many grams of CO2 are released to produce 1 kilowatt hour of electricity. For example, it can be ton of CO2 per megawatt hours, whatever unit, but we want to know how much CO2 emissions we have to produce a unit of electricity. How do we do that? We already calculated our total emissions for electricity generation by fuel. We just need to divide it by the electricity generation that we have already in our energy balance. So doing that, we see that coal electricity generation is much more intense as expected compared to natural gas. So you can see it's at least 2 times. So when you generate coal, electricity, for each kilowatt hours, you are emitting more or less twice than if you're using natural gas. As you can see, we have 600 grams of CO2 per kilowatt hours versus 1,200 more or less. And then you can calculate also the average in your country. How do you do that? It's not the average of these 2 figures because, pay attention, you add electricity production by other fuels that are namely zero carbon in this case, because we consider only the direct emissions and we exclude any biofuels emissions. So we have hydro, PV, and wind that come in play when you have the electricity total production in the countries. That has also their weight on the total electricity production, and they don't emit CO2. So when you calculate the average, you need to take the total electricity generation emissions that you calculated before, and you divide by the total of the electricity production. So including also all the other not emitting sources. For example, in this country, you can see that the average, we can see anymore the formula. Okay, that the average is a bit different than the average of only the carbon, the fossil fuels, because we are taking into account the others, and it will be lower because the hydro, the PV, and the wind electricity production is not emitting. I think I can show you the number if I achieve this kind of an Excel trick. No, it doesn't work. Okay, anyway, it's showing the formula somehow, but this number will be lower than the emissions per kilowatt hours related to fossil fuels, because we have this that counts 0. I think the exercise is done, and I already took a lot of time to do that. I'll answer any question if you have. I don't know if Arnaud has already. I cannot hear you, Arnaud.
Great. There is one first question from Gedeon Girma on question 3. So this relates to what we just said on refinery efficiency. So as Gianluca explained, in terms of energy unit, you cannot have an output which is higher than an input. You cannot have an efficiency rate above 100%. But in volumetric units, indeed, you can produce more products than what you have as input. So here, this table is in energy units, in terajoule. So you need to have an output which is lower than the input. But you took it right, Gedeon, that in terms of volumetric units, you can have output higher than input. Exactly. This was the first question, Gianluca, and there is another one on GHG emissions from electricity production.
How to estimate? But here we had to estimate greenhouse gas emissions from electricity production. We had a very simple approach. We know the input of each fuels used for electricity production. So we know how much coal, and better even will be knowing which type of coal is used, if it's lignite, etc. So we know this. We know how much natural gas, we know how much oil, we know how much hydro, etc. And for each of these fuels that is burned, we know how much CO2 emissions are released per unit of energy burned. So this is the CO2 emission factor that we can see provided here. But you have available from the IPCC guidelines and many other sources, the emission factors. But important to know is that you shouldn't use a factor applied to the electricity generation directly, but to the fuel that is combusted for the electricity production. So you have the input of coal that is burned in an electricity plant, and this, at this point of the transformation that you are gonna estimate your emissions. You're gonna say we are burning here 8,255 terajoules of coal, and we know that this is equivalent to 809 megatons of CO2 because we have the carbon emission factor of coal. I don't know if this was the question, and then to estimate the indicator on the intensity of electricity generation, we need to firstly calculate this amount. So how much of each fossil fuels is consumed or burned to produce electricity, multiplying them by the carbon emission factors. And so we'll have the total emissions by electricity generation, caused by the electricity generation. And then we can divide this by the total electricity production, that is the output. And this will give us an interesting indicator. You can see this country has 815 grams of CO2 for each kilowatt hours that is produced in the country. There are some countries like Ethiopia that has a much lower number because you have practically all your electricity generation will come from hydro, some renewable energy, and really few from combustible. So the same indicator for Ethiopia will be probably very close to zero. I don't know if this was the question. I hope we answer. But when you say GHG, maybe you wanted greenhouse gases. You wanted to include also the gases that are not only CO2. There are, of course, methods to and also direct conversion factors that can tell you how much of all these other gases like methane, etc., are related to CO2 emissions in the electricity production. And of course, depending on the analysis you do, you might do different analysis because the electricity generation real emissions are not only coming from the combustible, from the fuel that is combusted. They're coming also, you might say, from the extraction of coal. So you want to analyze the upstream impact on CO2 emission of coal extraction, transportation, etc. This will be a life cycle analysis approach that will take into account the whole value chain of electricity production from fuel extraction, transportation, to the plant production, to recycling. But this is not the purpose of national emissions reporting because these emissions will be included in other lines. For example, coal transportation will be included in the transport of fuels as well as natural gas. Here we have no numbers because it's a fake balance, but normally you have all these emissions related to another flow. For example, coal mining will have a line somewhere here in between transformation and final consumption, and coal mining will consume some energy, and this energy will be related to emissions. As well as natural gas, sometimes when extracted, many times, when extracted is leaked, when its transport is leaked, so methane is already going in the atmosphere, and this is another reason of GHG emissions. But I would like to keep it simple and just focus on the balance CO2 emissions related and how we calculate it on national level using this approach. So we take into account the inputs of each fossil fuels, we use the conversion factor, and like this, the carbon emission factor, and like this, we can estimate the emissions by each source of energy that is used to produce electricity. I hope this was clear. I think we can pass to the next exercise if there are no other questions, and there are no, can continue for the today webinar by solving the exercise on modeling and the example of transportation that is really interesting as well to follow really with attention. Thank you very much. And I hope you have other questions. We'll be happy to answer at the end. Keep writing them in the question and answer, please.
Thank you, Gianluca. So let's start with the exercise number 3, which looks into modeling. So here there is some questions we want to answer on the regarding the futures, which is what will be the demand for oil from the transport sector in 2 years, in 10 years, in 2030. So we are really entering into this projection and modeling parts. But to do modeling, first we need data, and this is something we will never emphasize enough on, is that we really need reliable historical data to be able to do modeling. So in this table, we do have socioeconomic indicators like population. We have data and input data relative to the transport sector. So you have the total car fleet, the car stock, the distance traveled per car, the occupancy rate per car. You also have some data regarding oil demand for transport, but also oil supply. And this file is structured in a way where you will have this data per line, and you would have on these columns historical data and then projections. So last thing before I start answering the questions, it is a very simplified model. As we discussed in the modeling webinar, we need to take assumption, we need to make simplification, and what we did here is that we consider that 100% of the oil consumed in the transport sector is consumed by thermic cars for passengers. So we do as if there were no bus, no trucks, nothing else than passenger cars. And we also consider that there is only one transport fuel, which is gasoline, which obviously is a simplification. So once we've done that, we could, in a second row, we could make it more complex, but for now it's narrowed down to one variable of activity and one fuel. So this said, let's start looking at the questions. So questions 1 and 2 are related to statistics, and before doing projections, we need to rely on good statistics, and we need to get a better understanding of what the reality of the transport sector and the oil demand for transport is. So question 1 is asking us to calculate an indicator that will give us a very good idea of activity for passenger car transport, which is the passenger kilometer variable. So we discussed this in last Monday webinar, and basically to calculate it, this passenger kilometer indicator, we have to take, and I will do the calculation live, we have to take the total number of cars. So here it's written in millions, so I directly multiply by 1 million. We multiply this by the distance traveled per each car and by the occupancy rate. Sorry, the occupancy rate. So here we'll have a passenger kilometer, but we want it in billion kilometers, so I divide it by 1 billion. Okay, so this is the indicator for our historical period, 2000 to 2018. Question 2 is, now that we have this indicator, let's look at another one regarding the oil demand and the average fuel consumption per car. So how do we get this average fuel consumption per car? Well, it's quite easy, because we have the total oil demand, and we assume that all the oil is going to this activity. So we take this oil demand, which is in kilo TOE. So I multiply it by 1000 to get TOE. And we divide it by the total number of cars, again, by million. So by 1 million, multiplied by the distance traveled per car. So here I have an average fuel consumption per car. I will expand the formula, which is expressed in TOE per kilometer. But as you know, TOE per kilometer, it's not a very obvious indicator. So what we can do is to convert it in something we are more used to hear about, which is liters per 100 kilometer. And here we have a conversion factor. So a best practices in your Excel files is as soon as you have a conversion factor, instead of writing in the cell of your formula, write it down somewhere, like in this column, and refer to this cell so that it's more obvious and explicit for everyone. So we just have to convert. I will do here. So from TOE per kilometer to liters per 100 kilometers. Okay, so now we can see that the average fuel consumption has been decreasing over the last 2 decades. So those 2 questions were about statistics to get a better understanding of the reality of this transport sector and oil consumption for transport. Now we can start looking ahead and looking at the future. So question 3 is, what will be the total fleet of cars in the coming years? How will this evolve? So here, to calculate that, we need to take assumptions. And this is something we stressed a lot, that we cannot do projections without assumptions. Hence, the need for having some clear assumptions, to be transparent on them, and to take them based on past trends, on the literature, and on things that can be rational. So here we are saying that we'll assume how the distance traveled per car will evolve over time. So first, I will just report the distance traveled per car historically, which is just above in the table. And then it is said that when we want to project it, the assumption is that it will increase at a rate of 50 additional kilometers per year. So again, I have a hard-coded parameter. I write it here. And then I will just add this number every year and project it until 2030. Then occupancy rate per car, it is said that it will remain constant. So I just take the value we had in the inputs table, expand it, and then, as we said, it remains constant. So no need to change it in the projection. Then passenger kilometer. So for the historical part, we will take the data we calculated at question 1. And how will this evolve over time? So what it said is that we need to take the assumption that passenger kilometer will increase at a rate of 7% per year. So again, I write my parameter in this column, and I will calculate a growth rate. So 2019 data is 2018 multiplied by a growth rate of 7%. And I will expand this to 2030. Okay, so we have made our assumption on how those variables will evolve over time. Now let's answer the question. We want to see how total car stock will evolve over time. So as we've seen in question 1, passenger kilometer is calculated from total car stock and other indicators. So we can do the way in the opposite way, meaning that we can calculate and deduct total car stock from a passenger kilometer. So this is what I did here. Basically, the calculation is, so total car stock is the passenger kilometer indicator divided by occupancy rate and distance traveled per car, which is just a basic formula of passenger kilometer that we take upside. And we can check that our calculation is consistent with what we had just here as a total car stock. Okay, it's true, so it's consistent. So my formula is working, so I can expand it to 2030, and here I get my projection of how the total stock of car will evolve over time. And what we see is that from 2018 to 2030, the total number of cars on the roads is to double. So now that we know how many cars we will have on the roads by 2030, we can ask ourselves, okay, how many gasoline will all these cars consume? And again, we need to take an assumption on the average fuel consumption per each car. This is question 4. So the average fuel consumption per car, we know the historical values. It was just, we calculated at question 2. We expressed it in TOE per kilometers. And then it is said that we need to take the assumption that average consumption per car will decrease by 1% per year due to efficiency improvement. So again, I will write here my parameter and calculate a growth rate or decrease rate to be more precise. Over time, I need to make sure my cell will not move. So this is how will evolve the average fuel consumption per car. So we were at 0.001 in 2000. It will go down to 0.78 in 2030. So we know how many cars we'll have on the roads, and we know how much gasoline each car consumes. We can easily calculate the total demand for oil. So I will make the calculation live. So total oil demand is number of cars, but I need to put it in numbers and not in millions of cars. And divided by the, no, sorry, okay, I will take the formula which was already done. So indeed, it is the total fleet of car multiplied by the distance traveled by each car and multiplied by the average fuel consumption. This was expressed in TOE. We want kilo TOE, so divided by 1,000. And we can also make a quick check. Is this value consistent with what we had in our input table here? Yes, it is. So our calculation is good. And I can project it. So what we see is that by 2030, the total oil, the total demand for oil will double as compared to 2018. So here you can see that with basic assumptions, we've been able to get an interesting information, which is how the demand for oil will evolve in 10 years. Okay, so now we know how much oil will be consumed. We can try to understand how will supply meet demand, given that there is some local refinery which provides some fuels locally, and that for the remaining needs, we have some imports. So it is said that we have refinery outputs. This was given in the historical input table. So I will get this value. And it is said that the refineries in the country will have an increase of 2% of their output per year. So let's put 2% and again, calculate here a growth rate, an annual growth rate, so that we are able to project how the refinery outputs will evolve over time. So by 2030, it is under our calculation, it will go up to 100 kiloton equivalent oil equivalents as compared to 81 in 2018. Okay, so we know how much oil the refinery will produce. We have calculated that question for how much oil we need. It's easy to deduct what we need to import, which is just the difference between the two. So again, I will check that my calculation is consistent with what we had in the input table. Oh, sorry. Yep. So is this equal to what we had here? Okay, it is, it's true. And from there, I will project to 2030. So under our model, we see that the imports of gasoline, if we want to meet the increase in demand and considering that the refinery outputs will increase by 2% per year, need to rise by more than 150%. So multiplied by 2.1. Last question we can answer and an indicator we can easily calculate is the import dependency. So we see that to meet our needs for the local market, we need to import more and more oil. What's the dependency rate? So here is just calculating what we import divided by what we need. So what's the demand? Oops, sorry. It's just the cell below. And here we can see that the dependency rate, import dependency rate, was at 53% over the last 2 decades, and it is set to increase to 70% by 2030. So with those 6 questions, we have seen a bit of how to calculate statistical indicators that reflect a given sector, so oil for transports and cars. We have also made some projections. Now the question that we can ask ourselves is, how did we take those hypotheses? Where does that come from? Because it's all the point in modeling is to question the hypothesis and to see the impact. So you have seen we have taken some assumptions. I have entered them in the parameter column. Let's look first at the evolution of passenger kilometer indicator. So we took as an assumption that this would increase at a rate of 7% per year between 2019 and 2030. Why have we taken this 7% annual growth rate? Well, it's basically that we have calculated over the last years. So, sorry, I calculated here. If we look at the evolution over a year, and I will expand all the historical years. You can see that no, sorry, I'm not on the good line. It's passenger kilometer, so I was supposed to calculate it here. Okay, so this is how passenger kilometer evolved year after year, and we can see that it rose quite significantly in the beginning of the century, and then a bit less. So what we did is that we took the last 10 years, and we saw that the average annual growth rate was 7%. So we have chosen to take 7%, but we may have said that we could have taken a lower rate, taking into account the trend over years. So this was to explain to you how we took this assumption. Now, what we can do is to look more at what could be done to change this future. And here we have taken some assumptions that relate to some policy, to something that governments have lever to change. So what would happen if there are efficiency measures that improve the average fuel consumption per car? What happens if the government develops more the refinery capacities and increases the refinery outputs? So to analyze sensitivities and to look at those questions, the easiest way to go is to make some charts so that we can directly see the impact. So here, under our projections, you can see how passenger kilometer increased, oil demand increased, while fuel consumption remained stable or decreased slightly, as we saw it was a 1% improvement per year. In this chart, you can look. It's a zoom on the total oil demand, which is increasing, and the average fuel, which is decreasing on the right axis. And last, here on this chart, we are displaying the imports of gasoline, and on the right axis you can see the import dependency rate, which is quite stable at 55%. So now, what if we change our parameters? Sorry, this was supposed to be 1%. Okay, so let's imagine that the government takes some very bold energy efficiency measures, saying, for example, that very old and inefficient cars cannot be on the roads anymore, that only recent cars or cars that are less than 10 years can be imported. And by this means, the average fuel consumption per car improves every year from 1% to 3%. And in parallel, let's imagine that the refinery output increases from 2% to 4%. And then what we can see is that the import dependency remains stable, while previously, with our previous parameters, it was increasing significantly to 70%, and the oil demand was really increasing fast. So I'm stopping here, but just to show you that we can analyze the sensitivities, and based on that, we can define policies to try to get where we want in terms of impact on the energy system. Okay, so I'm stopping here and looking if you have specific questions.
There are no questions for the moment. We had a question from Abdul, but I think you answered already quite well. It was about the assumption and parameters. I think you already gave an explanation of that. He was saying, if we don't have an uniform annual growth rate, can we use a compound annual average growth rate? And that's, of course, it's what we are doing here. The 7% is a compound average growth rate that you are assuming will be stable for the period. But of course, as Arno said, for each year or small periods, you can have different growth rates or assumption that you are using. For example, if there is a policy for 2025 and a different, more short term for 2022, you can apply different growth rates depending on the complexity of your model. This is a really simplified version for the exercise purposes. Now we have some time for your questions. I hope you will have some interesting ones. And if not, again, as all the time, send us an email or WhatsApp. So we will be able to provide you with questions, guidance, and maybe also some other tools, reports, etc., related to your needs. I take, while you write the questions, or I'll take the occasion to tell you about the program. So tomorrow is the last webinar of this introductory course. Of course, we are not finishing with our program because it's a 3-year program. So we'll continue to work together after the summer. We'll continue to work together in 2021 and 2022 to have many capacity reinforcement activities, but also other kind of activities like data collection, data improvement. We will work together on specific data if you have the occasion to try and improve them. Tomorrow, very important, we have a session on solid biofuels consumption with a specific focus of the residential sector and traditional use of biomass. So we also see the SDG Sustainable Development Goals on clean cooking access. And also we will see the other important topic for Ethiopia, that is access to electricity. And we will see the problems and barriers to collect data for electricity access, namely with off-grid generation and appliances for electricity production. We will see how we can model both demand in the residential cooking sector and how we can model access to electricity for